Nature produces fatty acids by a process that involves the elimination of water from beta-hydroxythioesters. The enzymes that carry out this reaction are known as dehydratase enzymes, and so that's the elimination of water across the 2,3 bond to produce this trans alpha-beta unsaturated thioesters. These trans alpha-beta unsaturated thioesters can be hydrogenated. That means the addition of the elements of hydrogen across that double bond to produce saturated fatty acids. Alternatively, that trans double bond can be isomerized by an enzyme known as isomerase to the cis double bond geometry. Those are rarely hydrogenated, so those cis double bonds stay in place, and the resulting fatty acids are what you know as unsaturated fatty acids. In this webcast, we want to look at the dehydratase enzyme step and try to understand whether this elimination proceeds by a syn or an anti-elimination process. And so if you just go ahead and draw in the implied hydrogen atoms at the alpha position, those hydrogen atoms are diastereotopic. We have the R configuration of this hydroxyl group here, and that differentiates the two different hydrogens as being diastereotopic, which you could determine if you did the Q test on those. That's important because when it comes to deciding whether the process of this pathway, this elimination pathway, is a syn or an anti-pathway, we need to know which of those diastereotopic hydrogens is lost and which one remains. So in order to determine syn or anti, there's actually two pieces of information we need. We've already determined one of those. We need to know what's the geometry of the double bond of the resulting product, and we need to know which of these diastereotopic hydrogens is lost, given that the configuration of that hydroxyl group is in the R configuration. Well, the way that a scientist would go about determining which of these diastereotopic hydrogens is lost is to label one of them with deuterium. Remember, deuterium is the heavy atom isotope of hydrogen. It behaves chemically just like hydrogen, but it can be distinguished spectroscopically from hydrogen, and so we would be able to know which of those two what appear to be equivalent hydrogen atoms would be lost in this product by labeling it with deuterium. So if we were to label HR, we would see that it's still in the product, and so it must mean then that the one that's removed is HS. And so in trying to decide whether this process is a syn or an anti-elimination, we need to think about what groups are lost. The elements of water come from the pro-S hydrogen and the hydroxyl group that are shown here. And so to decide whether or not the syn or the anti-pathway give rise to this double bond geometry, we need to position these groups as being either syn or anti to one another and ask which of geometry is produced from syn and which geometry is produced from anti. And the best way to determine that is by looking at a Newman projection, which is what we're going to do. Our stereochemical analysis is going to be examining from the view that's shown there with our eye positioned down the 2,3 bond. We're going to draw the Newman projection, positioning all of these groups exactly as the stereochemistry shows, with the R configuration of the hydroxy group and the pro-S hydrogen positioned either syn or anti to the hydroxyl group which leaves. And so here, the first one, we see that the pro-S and hydroxyl group are positioned in an anti configuration. Remember, that involves, in other words, they're going to be lost on opposite sides of the plane that will become the carbon-carbon double bond plane. And so if we notice what groups are on the same side of the what will become the carbon-carbon double bond, well, it's the HR and H, those are on the same side, and the carbonyl group and the alkyl chain. And so when the elimination takes place from the anti-conformation, that is, we just rotated that carbon-carbon double bond to put the hydroxy group and the HS anti to one another, we end up with the cis geometry. All right, we could reorient those groups so that the pro-S hydrogen and the hydroxy group are on the same side of that double bond. And in this case now, so there's the double bond. Try to imagine that those tetrahedral carbon atoms are going to squash down into a plane, and what's on the same side now of that plane would be the carbonyl group and the hydrogen atom. So we see on the one side is hydrogen and carbonyl, And on the other side of what would become the double bond, since these groups are jettisoned, so the same side would have HR and carbonyl, and that gives rise to the trans geometry. So the bonds that are drawn in red, those are going to be the opposite side double bonds, or bonds on the opposite side of this double bond. And since that's observed, we can conclude that the geometry of the elimination is syn, follows a syn pathway. Having concluded that, we can rule out that this is an E2 mechanism, because we know that the E2 goes by the anti-mechanism, and since we've seen that this geometry is obtained by the syn pathway, we know that this is not an E2 elimination mechanism.